My name is Brian Kasch. I'm from the Air Force Research Laboratory Space Vehicles Directorate. I work in a laboratory where we create states of matter that are as cold as anything in the universe, down to nanokelvin temperatures. Here today we're going to work with liquid nitrogen. It is going to freeze everything we put in it, make things break. So we're going to have some fun with liquid nitrogen today. This pie tin here is made out of aluminum. If I fill it with some liquid nitrogen, the cold that creates on the top surface easily gets transmitted down to the bottom. And what you see is that it starts to get really cold and it starts to accumulate some liquid. That liquid is not coming from me spilling over the top. I can watch and say, I'm not spilling anything. But you can hear that liquid is dripping. Well, what is that liquid? Well, it turns out it's liquid oxygen. Liquid oxygen condenses from a gas to a liquid at about 10 degrees warmer than liquid nitrogen. So liquid nitrogen is easily able to pull that gaseous oxygen out of the air and turn it into a liquid. And that's what's happening on the bottom surface of this tin. It's accumulating and dripping into this other tin. Liquid nitrogen is at 77 degrees Kelvin, which is negative 196 degrees Celsius. That's very, very cold. So what you're going to see when I pour this, you're going to see that it looks like boiling water. The reason it looks like boiling water is because the room we're in, at room temperature, is like a hot oven. So it means that this liquid nitrogen is constantly going to boil whenever we have it out in this room. One of the things that's really nifty is if we take a little bit of this and pour it on this table here, it'll roll right across the table, slide on the table. What's happening is it's riding on its own cushion of air. So you may notice that I didn't use a glove on my hand when I was pouring the liquid nitrogen there. If I stick my fingers in liquid nitrogen, there's an effect that actually protects my fingers. My hand is so warm that it actually flash boils the liquid nitrogen and forms a little vapor pocket that protects my fingers from getting frostbite. As long as I'm careful, I will not wear a glove in certain situations because, believe it or not, it can actually be safer. The glove can absorb liquid nitrogen because it's a fabric, whereas for my hand, it just rolls right off. One of the things we talked about is that liquid nitrogen is very cold, and that has to do with the average velocity of the atoms and molecules in the air in this balloon, for instance. So what's going to happen when we cool them down? Well, what's going to happen is we're going to slow them down. This balloon is mostly full of nitrogen because, after all, air is more than 70% nitrogen and only 20% oxygen. So as we cool the atoms and molecules down, mostly molecules, what's going to happen is that they're not going to run into the walls of the balloon with as much velocity, which effectively means that they're not pushing on the walls of this balloon as much. But the air around the balloon, outside with us here, is pushing the balloon just as much as before, and so it causes it to shrink. Now what's really neat is that if we wait long enough, the air inside here will actually liquefy. And if we were to look closely, we would see there's a little bit of liquid in the bottom of that balloon, but let's see what happens. Now, do you think the balloon's gonna pop? Because I'm not so sure. I will say that even though we don't expect the balloon to pop, it has happened before, so we'll just have to see. Sometimes we get cold spots on the balloon. It expands fast enough that it actually just pops. Well, now you can hear the liquid. Okay, it's all starting to come back to air now, and we see that our balloon returns to normal. Okay, now we have another balloon, except this balloon is filled with helium instead of air. And as we all know, helium in a balloon like this will float away if you let it. Now let's see what happens when we dip it in liquid nitrogen. So we know that nothing is escaping from this balloon, right? We already checked that with the other one. It blew right back up to its original size. If we have the same amount of stuff in a smaller volume, what it means is that we've increased the density. And so now the question is it still going to float in air? Let's find out. So it sinks until it warms up again. Then the density drops enough that it floats again. We saw earlier that when we put a balloon filled with air and liquid nitrogen, it shrank. Well, at the same time, when you take a liquid and let it boil off into a gas, it expands, and expands by about a factor of 1,000. So with just this small amount of liquid here at the bottom of this cup, we will be able to fill this balloon and pop it. Now, we used to make the kids do this. We would choose 2 volunteers. Each of them would stand in a corner holding a cup just like this with a balloon in it and shake it around. And the one that could make the balloon pop first would win the so-called balloon race. Wow, it's loud. Here we're going to demonstrate an effect called high temperature superconductivity. This is a particular material, in this case YBCO, and this YBCO material, when we cool it down to liquid nitrogen temperatures, it will carry electricity perfectly with no loss whatsoever. What that means is that as I bring this magnet in and I push it down into this material, something interesting is going to happen. It levitates. The reason for this is complicated. It's not a simple explanation. YBCO is called a type 2 superconductor, and this type of superconductor, nobody really understands what's going on yet. It's an active area of research. For type 1 superconductors, we have a pretty good idea. What's happening is electrons are talking to each other through this material. So when an electron moves in one way, an electron a few microns away from it might move in the opposite direction, and that particular coupling forms something called a Cooper pair between those electrons, and that is what is responsible for type 1 superconductivity. In this particular case, what's interesting about a superconductor is when you push a magnet or magnetic fields into it, it actually generates an electrical current that opposes that. So as the magnet gets closer, it generates an electrical current that wants to push that magnet away. What happens when we cool things down with liquid nitrogen in general is they become much, much more brittle. So now we're going to demonstrate some of the things that we can break with liquid nitrogen. These are going to boil like crazy when we put them in. Okay, so we're going to take this huge rubber band and stretch it onto this ruler here, and then dunk the ruler in liquid nitrogen and take it off and see what happens. Should just about do it. Now, this part's not so cold, so I can peel it right off of there. Now let's look at the rest. The brittle rubber band. Come on, banana. Whoops. It's not showtime yet. One of the questions that some students ask is, can I eat that banana? And the answer is you don't want to eat it when it's that cold. I've tried eating grapes before that are nearly this cold. What happened was it just froze to the inside of my mouth. Like when you lick a metal pole in the winter, So I got a cold burn on the inside of my mouth from eating something that was too cold. So you have to be careful. One of the things we've noticed is how brittle things get. One of my favorite things to do is to crush a flower that has been frozen. So it doesn't take very long. Since the leaves on a flower like this, the petals are very paper-like when they're cold. So it just takes a moment or two to freeze it. And that's what you get. Okay. Just a normal racquetball. I'm going to demonstrate how brittle a racquetball can become when it's cooled to 77 degrees Kelvin. That's one of my favorite things to do. Last but not least, I want to show you what happens when we take some nearly boiling water and throw it into liquid nitrogen. Well, thank you very much. My name is Brian Kasch. I work at the Air Force Research Lab, Space Vehicles Directorate, and I have had an absolute blast showing you liquid nitrogen and all of the mess that it can make.